Where were we last time? We were with this bounded input, bounded output stability, and we were looking at how LTI systems characterize in terms of BIBO stability. Bounded input, bounded output stability is a stability of an equilibrium point. True, false, I do not know. Whenever I talk about BIBO stability, am I talking about the stability properties of an equilibrium point? Yes, no, I do not know. Very much no. I'm talking about the system. Okay? Together? So, bounded input, bounded output stability means that in a certain sense, I check if the inputs, depending on whether it's bounded or not, whenever the input gets mapped into the output, I want to understand if the boundedness preserved. For example, if I've got a system for which I start from this signal and I get to this signal here, this one, will it be BIBO stable? No. And if I do an experiment and I start from here and I end up here, can I conclude that the system is BIBO stable? No, I cannot conclude because I need to do it for every signal. True? And if I do something for which I start from here and end up here, can I conclude something? No. If I do this, can I conclude something? No. It's starting from bounded input. If for any bounded input the system maps me into a bounded output, then that one is a BIBO stable system. Okay? Together? HDMI 2. Perfect. BIBO stability. I can talk about BIBO stability only for LTI systems. True, false, you do not know. 1, 2, 3. Discuss. Do you know it already? You should know it already. False. BIBO stability is for every type of system that has an input. True? Perfect. Why are we focusing on LTI systems now? Because LTI systems is easier to characterize LTI systems. In a certain sense, we have that an LTI system is BIBO stable if and only if its impulse response is absolutely integrable. In the sense that whenever the area of the absolute value of the H is finite, then in a certain sense we are assured that starting from the kernel of the first avocado, we will end up on the kernel of the second avocado. Okay? Let's make an example. If I have h of t that looks like this one, time h of t, and we do it in violet. This one, this signal here, how does it look? It looks like a signal t for t bigger than 0, 0 otherwise. True? This one. Is this signal here absolutely integrable? Definitely not. True? If it is not absolutely integrable, it means that my system is not BIBO stable. True? If it is not BIBO stable, this is an exercise that I'm going to give very often at the exam. Okay? If a system is not BIBO stable, it means that there must exist some input that is bounded that has to go to an unbounded output. True? There must exist at least one. True? Are we together on this? 1, 2, 3, people. Exercise at exam, find it. An exercise for now, for you to do it. There's a question before. This is all the potential inputs, and it's something that you decide. And I can choose. This is an input. True. So there will always be some inputs that are bounded. True. So think at all the continuous inputs. Let's make it very simple. We can go more sophisticated, but take this avocado to be all the continuous signals. Now, let's do this exercise together, and you've got to think a little bit. How do we get the output? We do the convolution, true? You remember the convolution, how it works? Shall we check a little bit more? Let's go to Edge, Swarthmore convolution. We remember this thingy, true? The area is the value. And here, this is the output. This is the flipped impulse response. Black is now, true? I do the multiplication and the integral, true? And here we have something that is constant, starting from this impulse response and this input, because in a certain sense, whenever I'm enough inside the rectangle, that area is going to be virtually constant. Do you see it from an intuition point of view? Perfect. Now, the H is this one, okay? It means that in a certain sense, instead of having this, you're going to have something that is a ramp, okay? Think at an input. No, what is happening now is going to do the... Okay, didn't do. Excellent. Think at an input that is bounded, that gets mapped to an unbounded output. Go. Is the question clear? You've got to find U, that is H, that is given. You've got to find U bounded that leads me to an unbounded output. Okay, people, I do it. We are going to do another couple of exercises like this one, okay? So don't worry, I'm cutting it short, but let's see it. So what do we have to do? This one is fixed. Let's put it in the simulator. The H is going to be a ramp. Where was the ramp? There must be a ramp. Ramp. Okay, imagine a ramp that goes forever, okay? Imagine a ramp that is going on forever. What is happening now that doesn't work anymore? Oh, signore. And think at an input U. There is something that you select, true? You might select this one, you might select this one, you might select something like this, true? Think at a step. If you think that the ramp goes on and on and on, what are you going to have? The area that is the output is going to be something that looks like a quadratic. True? It's the area of the triangle that is increasing, increasing, increasing. The triangle defined by now up to 0. You see it? Do you see it, people? 1, 2, 3. Okay. Now, let's take H that looks like something that looks like, this is an important example, okay? This one, you've got to remember it for the, something that is looking like 1 over t plus 1 for t bigger than 0, okay? This is my h, okay? This h here, is it absolutely integrable? Yes, no, I do not know. Okay, people, the integral of 1 over t, the integral of 1 over t is logarithm of t, true? Logarithm of t for t that goes to infinity goes to plus infinity, true? Together? This is how much paint do I need to paint this wall? An infinite amount of paint. Is this one absolutely integrable? No. Together? Is the LTI system defined by this impulse response BIBO stable at this point? No. True? Because it's not absolutely integrable. Crash. Don't ask me why, but there's been some crash. Are we together that if I find that H is not absolutely integrable, it means that I'm not BIBO stable? Are we together? Perfect. It means that, where am I? Oops. It means that somehow, given this impulse response that goes down but not fast enough, there must exist at least one input that is bounded that leads me to an unbounded output whenever I do the convolution. Are we together on this? 1, 2, 3. Perfect. Find that input. If this U bar must exist, find it. Go, let's go. Okay. Somebody wants to answer which U is U bar? Which bounded U leads me to an unbounded force response? Unit step, as before. What is happening? This is an exponential, okay? But imagine that it's 1 over t plus 1. You are gonna do this convolution, true? And you've got U that is a unit step, and basically, essentially, you got for every now, you have the area of the impulse response between 0 and now, true? You see it? If you think that this area here is the area between 0 and now, if you think in the tau coordinate system, true? Are you following me, people? 1, 2, 3. In the tau coordinate system, this is 0 and this is now. Okay? And this area gets bigger and bigger and bigger if we have a logarithm, or better, if we have 1 over t, this stuff here will keep increasing, and it will behave as a logarithm, and it will go unbounded. How much are we together? I would like everybody to answer always how much we are together, because in this way I know how to go. Okay? Perfect. Now, let's do something more fancy. I have an H that looks like something like before, okay, as now I continue drawing. It's actually 1 over t plus 1 times sine of basically that sine of t floor t. Sine, no, sorry, minus 1 at the sine of floor of t. Do you get the point? I'm kind of making it minus 1 at sine of the floor of t or ceiling of t, okay, times the same as before, so that we have basically the same function as before, only that it goes, how do you say it? It's kind of broken, goes up and down. Do you see it, people? 1, 2, 3. I'm drawing it in a bad way. This is my 1 over t. True? Now, copy, paste, turn. Yeah, I got to do some magic, but you get the point. Okay, together. And then I take together. Are we together? Etc. 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 Okay. Blah 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 blah. Do you see it? 1, 2, 3. Perfect. It's basically the same as before times a number that is minus 1 to a power that decides whenever it's positive or negative. You see it? Perfect. This one, this h of t, is it absolutely integrable? Yes, no, I do not know. No, because if I take the absolute value, I get the stuff as before. So are we together that if I've got to consider absolute value of h for the BIBO stability test? The BIBO stability test is about the absolute integrability of h. This one is not absolutely integrable. It means, what does it mean? It means that there must exist a bounded input that leads me to an unbounded output. We are together on this. True? Is before we were having u as a step that was working. True? True? U as a step. Is it the stuff that I'm looking for? Yes, no, I do not know. Is that U, that is the step input, that is a bounded input, is it going to bring me outside or inside? 1 outside, 2 inside, 3 you do not know. No. Uh, So, what would you say, people? What would you say? Inside or outside? Inside. Why? What is the integration do? Imagine this one to be as before. Imagine the red one to be as this one. Okay. I don't have the graph. I should have done the graph. But imagine this one. What happens? As now goes inside, I've got area, area, and then again area, area. Whenever you have the step, what are you computing as output? The output is going to be the area of the impulse response between 0 and now. True? Do you see it? That somehow whenever you do the convolution with a step, eventually what you're computing is just an area. Do you have a question? Let me finish and then I'll take the question. So whenever I do the convolution until 10 seconds, I'm going to get as a value this minus this minus this plus this minus this plus this. True? Do you see that that value there as now increases, this is going to be finite? Just a moment. Just a moment. Let me do something that is going to be, let's do something that is damped sign. Damped sign. If I take this object here, whenever I take any finite value here of now, the area that I get, is it going to be finite or infinite? Finite. Then I do, whenever I move to a next cycle, what am I doing? I am summing and subtracting, summing and subtracting, summing and subtracting. True? This one it's true that actually it's not guaranteed to converge. It's not guaranteed to converge. In the 1 over t case, it is. It's going to be, because it's a differential one. You are not taking the logarithm anymore. Don't get the logarithm anymore. It's true that it's not guaranteed to converge. But you see that it converges more than before. True? You see that it converges more than before. In a certain sense, the ratio, the conditions for which you have that it goes to infinity, is that you need to have basically a certain difference in the areas that you get that has to behave as 1 over t, essentially. Has to behave as at least as 1 over t, in a certain sense of the area that they are increasing. Excellent. I think, did you want to point out this one? Yeah. Perfect. Did you want to point out this one too? Perfect. Yeah. I should have prepared some numerical example, but in a certain sense, you see that somehow, are we together that we have something for which, whenever the blue is a step, the stuff that I get is an area. The importance of having your own simulators is very underappreciated by myself. Anyway, if I have this object here, something, I guarantee you that basically the step is not going to be making you converge. Okay? Are we together? Believe me, I am sure 99% that I will have convergence. Okay? If I take an input that looks like this one, if I take this input u, you see it, how it's done? Something that looks like this one. What is going to happen? This one bounded. This one is bounded. Do you remember the video that we were having, YouTube? The video that we were having with the sinusoids. What was happening with the sinusoids? I re-put it. Well, I can also put it here. I can also put it like sine. But I'm incredible. I was remembering that there was the sine there, but it's not there. Playlists, convolutions. This one, whenever we have cosine of 10 times 10, whenever we have two signals that somehow go up and down with the same frequency, what is happening? We have this kind of constructive behavior for which things resonate. If you think at the green one to be this function and the blue one to be this function, imagine how they behave. You see that in a certain sense, whenever the crests are aligned, like here, sorry, this is the wrong. You see that the numbers are wrong. They are slightly off. Let's go back to the previous video. Whenever things are aligned, what do we get? We get a situation for which the minuses multiply and become plus, and it's equivalent whenever the crests are there. It's equivalent at having the situation that I would have gotten considering this one. You see? Do you see it? Only in that moment. True? Only in that moment. But if I shift of a half a cycle, you see that I'm shifting half a cycle. What happens? There are going to be situations for which we have this situation here, true? This situation here, like, and the other situation is going to be the opposite, true? And you see that somehow, if we take violet situation, it's going to have everything like minus. If we have green situation, everything is going to be up, plus. Do you see it? And indeed, if you think at this animation here, you see that it goes up and down, up and down, up and down. True? It means that the output is going to oscillate. Do you see that the oscillation is going to be there whenever we have this kind of stuff that is with, how do you say, sine waves types of behaviors? You see it? This is basically telling us that we are not going to have like a convergence to a certain value plus infinite or minus infinite for the output. We are going to have something that goes up and down, and will oscillate. Okay? So, what is the difference between this case and this case? You got the point. This one, the output will diverge in this way. This one, the output will diverge in this way. You get the point? But both are not absolutely integrable, bounded, diverging in the sense of unbounded both. Together? Okay? This condition here is essential, and from a graphical perspective, I hope that you see what I'm kind of highlighting. If we have this absolute value of 1t plus 1 with this fancy sign in front of it, I'm not going to take as a probe this, but I'm going to take u times the fancy sign. Okay? Together? Perfect. Sinusoids, examples, and I think we are there. The question that before it was not asking.
In general, how can we see, for example, we have the case of before, also with the sinus, if the difference between the two areas, the one on top, the two areas that must be the minus diverge or not?
I think you shouldn't care too much about this, at least for the exam, but also in general, to be honest. H, you take H. Is this one integrable? That means, is H absolutely integrable? If yes, BIBO stable. If not, not BIBO stable. Then at the exam, I'm going to give you something very easy, in the sense that if you know that this H is this fancy logarithm, you know that since it goes up and down, you need to take a u that goes up and down. You get the point? We are together? Perfect. Exercise by yourself. Decide. BIBO stable, not BIBO stable, you do not know, and a table for case 1, case 2, and case 3. Case 1, case 2, and case 3. Go, discuss. Okay, people, let's focus on the first one. How is the first one? How does the impulse response of the first one look like? It's E alpha t, true? In general, for first order systems. Here alpha is A is what? 0. Which system is this one? This one is an integrator, true? How do I find the impulse response of an integrator? As an input, I put a delta, direct delta. That means as an input, I do a direct delta, true? And the output is going to be what? The integral of the past, true? The output is going to be static, true? Do we see? How much are we together on these people? 1, 2, 3. H of t, f of t impulse. So this is my input, true? This is my input. I'm doing it in the opposite way. Let me do it here. I do it in the right way. Otherwise, I'm kind of making it a bit confused. I have a system for which the equation is what happens in the u, my output is going to be the integral of that u. Let's drop b. We can also put a times b here. U, this gets multiplied by b and goes inside an integrator. Are we together? You see it? Perfect. Integral from minus infinity to now. Y of now is going to be this integral here, u of t dt. True? Together? Are we together on this? Perfect. If this one is from minus infinity to 2 minus 1 of something that looks in time a Dirac delta centered in 0, this integral here is going to be 0 because I'm taking basically what I find until minus 1. True? Are you following me? Are you following me? Perfect. If I do until plus 1, it means all the stuff that I see until plus 1. True? This one is going to be 1. True? Because I'm including this one. Are we together? Until 5, 7, 10, whatever it is. What are we going to have as an output? This one is going to be a step. And since as input I'm putting the impulse, the output is going to be the impulse response. True? Whenever here I put the impulse, this one is going to be my impulse response. Together? How much are we together, people? 1, 2, 3. Question. The impulse response is the output to the impulse. Let's see if you see it. Which ODE do you need to have a ramp? Let's see if you see it. I think you should kind of let's see if you get it. I want a system. I want some ODE, some dots here and here, an LTI for which my impulse response has to be a ramp. What is a ramp? This is the integral of a step. True? A ramp you need to integrate twice. If I integrate twice the input, my impulse response is going to be a ramp. The question that you were asking, let's go back to the question that you were asking. I have a system. I inject an input that is a delta, Dirac delta, and as an output, I get an impulse response. Are we together on this? Perfect. If I tell you that a system is characterized by a certain impulse response, am I saying that I've got to put here inside a certain specific input? No. I'm only saying that whenever I have this impulse response as this system here, it means that in the past, somebody has been throwing inside a delta and got that H. Or made some computations, because you can also do computations by hand. Okay? And of course, once I know H, I can put another U here, any U that I want. Okay? Are we together on this clarification, people? H is a descriptor of the system. I can describe the system through H. Are we together that to this ODE, we have this impulse response, the light blue? Is this one absolutely integrable? Definitely not. Which bounded U will bring me to an unbounded Y? Another step, true? And I will get as Y a ramp. This one, this case here, is this one bounded input, bounded output, stable? Yes, why? Because this one corresponds to an impulse response that looks like EAT with A negative. That means something that is like looking like this. True? Area of that stuff, finite. Together? Are we together? That means BIBO stable. Question?
Yeah, I mean, like, we've not seen until now is the thing of like seeing the differential equation and look and retrieving the impulse response. So maybe if you can like go deeper a bit on that, because for example, the first case I understood, but this one, if I see straight away,
We are going to see one module dedicated on how to compute impulse responses very, very soon. Okay, in the not this one, the next one, but in 2 modules we start seeing that. The stuff that I would like you to remember for now is that whenever I've got an equation, an ODE that looks like this one, the exponential is the solution. True? Because the exponential is like you take a signal that is an exponential, I derive it, and I get the same signal. True? So do not worry about not being able to find H for now. You're not going to be able to do that until a certain moment in the course. But for the first order systems that are easy to do. Okay? Together? So this one, BIBO stable, because EAT with this one negative, absolutely integrable. Together? This one, BIBO stable, not. Excellent. What about nonlinear systems? Can we talk about BIBO stability for nonlinear systems? Yes, but not with the tools in this course. Nonlinear systems, you will see. Okay? Perfect. Two misconceptions that I see at the exam very, very often, and I hope that I do not see this time. Read those two and tell me if we are together. Very much together, not at all, kind of. Okay? I see some tools. The tools relate to this one or this one? Like other questions. What is not clear, people? This one should be very clear. This one is, it's not that if it is BIBO stable, then it has to be LTI, because LTI is only for LTI systems. Only, how do you say? Because BIBO, we know how to compute BIBO stability only through impulse responses. It's kind of a follow-up of the first one. Okay? Anyway, things that you don't need to know for the exam, and we do talk about stability because we are control systems engineers. We are going to stabilize unstable systems. Perfect. Well, I think we should have them. Let's see this one. Let's see this one. But they are relatively simple. Let's see this one, then we take a pause. And show me with the fingers whenever you are there. And everybody says 4. Excellent. Excellent. Very good. I think we are there. Perfect. People, are there questions? If not, let's take a